All right. Welcome to the Machine Learning and Data Intensive Computing Research Lab Open House. My name is Qiyu. I'm a professor from the School of Information, Horizontal College of Computing and Information Sciences. And together with me today is a group of my PhD students who are going to introduce themselves before their talks. Today we'll introduce some of our major research work in the area of AI machine learning. Okay, I will start with a high-level overview of the general research directions being pursued by my research group. I would then describe the two research projects that we are currently working on, one of which is funded by the National Science Foundation, and another one is funded by the Office of Naval Research under Department of Defense. Then multiple lab members will introduce some representative research areas in AI machine learning, including active learning, multiple instance learning, meta learning, and multimodal data fusion. We have at least one or multiple PhD students working on each of these areas, so we'll be able to demonstrate some of our progresses as well. So there are two central research themes being pursued by my research group. The first direction we are working on is to develop interpretable statistical learning models that can be used to analyze large-scale multimodal dynamic data with limited supervised information, as getting supervised information is really much more expensive. The second direction is to keep human in the loop, being able to show the modeling outcome to humans and incorporate human feedback for continuous model improvement. For the application areas, we are mostly interested in knowledge-rich domains, including medicine, bioinformatics, military operations, and so on, because problems from these domains are much more difficult to solve. This actually represents some of the hardest problems in machine learning. By working on these research themes, we hope to make some fundamental contribution that help advance the frontiers of AI machine learning. There are currently 13 PhD students working in the lab, focused on different aspects of these two research themes, along with interesting real-world applications from knowledge domains. I'm also supervising a good number of master capstone projects. All the PhD students in the lab are involved in these two major research projects. The first project is funded by the National Science Foundation under the Information and Intelligence System Program. The goal is to utilize synergy between human and computer information processing for complex visual information organization use. We have been working on this project for a little bit over 2 years. It will run through 2022. The second project is funded by the Office of Naval Research. In this project, we'll develop a multimodal dynamic Bayesian learning framework to support complex decision-making in military operations. This project will last for 4 years, and through this project, we are also collaborating with many other faculty members from RIT with diverse background that go beyond AI machine learning, including, for example, human-computer interaction, image processing, computer vision, and software engineering. So the central research task in the SF project is about the complex image understanding in specialized knowledge domains such as medicine, bioinformatics, security intelligence, such as surveillance in the airport, and so on. The figure shows an example of a dermatological image using existing computer vision-based methods. It should not be too difficult to recognize this is a hand. However, it may miss four important areas highlighted using the red boxes. The color, shape, and the distribution of these areas provide important information for medical professionals to make diagnosis. Therefore, in order to gain a deeper understanding of these images and help complex decision-making, such as making a diagnosis, it is essential to bring human expertise into the loop, and novel research needs to be developed as it is a highly non-trivial task. In our work, we use the methodology just as a case study, but the proposed research can be applied to many other complex visual problem solving applications where integrating human intelligence and machine intelligence is essential. So the overall goal of this project is to integrate human and computer capabilities to discover image semantics by first encoding image inspection and analysis behaviors that represent domain expertise. And then second, algorithmically fusing human expertise with image data for better image understanding. The primary goal of the ONR project is to explore a multimodal dynamic Bayesian learning framework to facilitate the complex decision-making in various highly complicated military operations. It will provide a comprehensive decision support in full innovative and integrated ways to maximize the overall effectiveness of complex decision-making. This also corresponds to the four major research tasks in the proposed project. In particular, the first task is to analyze large-scale heterogeneous and dynamic data streams from multiple sources and extract high-level and meaningful features. And then these multimodal features are fused in task 2 using Bayesian multi-kernel learning to provide decision recommendations with interpretable justifications, uncertainty evaluation, and also the estimated loss or risk to prioritize multiple missions. Task 3 is to identify sources of uncertainties and offer informative guidance for cost-effective information gathering using active learning. And finally, in task 4, we're going to visualize the model outcome and allow intuitive interactions with a human decision-making team to achieve human-machine collaborative decision-making. Each research task will address some fundamental challenges and has the potential to advance AI machine learning in these key areas. Also, the proposed framework is broadly applicable, right, to many other science and engineering domains where large volumes of complex data are collected in real time that go beyond human capacity to fully comprehend and manage. Okay, I think with that, that's kind of a very high-level overview of the current major research areas and the funded research project being conducted in my lab. With that, I will transition to my PhD students. They're going to talk about a set of representative research topics being pursued by our group. I'll turn it to Weishi, who'll be the next one. We're going to talk about our work in active learning.
Okay. Professor, can you make me the host?
Okay, yeah.
Share the screen.
Go ahead, yeah.
Okay. Oh, can you see the screen?
Yeah.
Okay. Oh, hi, everyone. My name is Weishi, and today I'm going to introduce the active learning in a nutshell. So basically, just introduce what active learning can do to help a machine become more intelligent in the learning process. And it's going to be very superficial and for our audience. So hope you enjoy that. So before I introduce the active learning technique, let's just have a very like a general view of the modern machine learning techniques and how they developed nowadays. So what can modern machines do in these days? They can play games, and as you know that in terms of performance, they for many games, the machine already exceeds the human behavior or human performance, like the chess, the Go, those simple games, the human master's behavior already been beaten by the AI. Like in chess, it's beaten by the IBM Deep Blue in 90s, and like in the like after 2000, the AlphaGo developed by Google also beat the human master playing Go, and the machine is becoming more and more evolved to play even more complicated games like those strategy games called Dota 2 and the StarCraft. So companies such as the OpenAI, funded by I think Elon Musk, and also the Deep Mind, it's a branch of Google. They start to looking at those fields that have very complicated behavior interaction of environment and making machine have a intelligence in that in those fields, and the machine can also drive and race. Here is a graph picture of the winner of like a few years ago, the Grand Challenge. This car is autopilot, auto-driven by itself, and it won the contest developed by Stanford. It also can translate and listen to human languages, like the Google Translate is a real-time API app that can just take any pictures and translate the context from the picture for you. And the Microsoft speech recognition now also reach the human level behavior, like they can real-time translate your words and even mimic the voice of the speaker. And for medical domains, there are also exciting progresses. For example, this deep latent deep lesions learned application allows you just take a picture of your skin and have a very accurate, sometimes even greater than the human experts behavior diagnosis for your health, for your skin health. And this is done by the deep learning algorithm. So, and there are also many more exciting machine learning applications in this field, and they are developing very fast. So, what's the potential problem, or how, why the AI techniques start to boosting in these recent years? I mean, before 90s, they are just slow, and we cannot imagine they can ever compete to human behavior. What makes the things so different? The answer is the data. So nowadays we are the data can be generated every seconds from the sensors, from the internet, from those modern techniques, and the data is said to just like the oil to the car. The data is like the can drive the modern machine learning algorithm to make them behave much stronger. And the more intelligence a machine is, like the deep learning, the more data they crave for. But why the data causes a problem? It's because like the raw oil, the raw data cannot be directly used by machines. Neither the raw oil can be used by car. They have to be refined, or the data have to be annotated to make use for the machine. So the problem here is the raw data is plenty and cheap, but to label them is very expensive. The reason is sometimes we need domain expert to label them, and it's high, expensive to hire them, and also even if you hire them, it's the annotation process can be very tedious, because for some domains, like in medical, it's hard to annotate in one data instance. So the traditional machine learning works in the following way. You have a bunch of raw data here, and the expert pick some of them, label them, and feed to the machine, so the machine can learn from the data. And because you have almost infinite number of raw data, and it's like to find the needle in the sea. to actually let the expert to find those informative or valuable data from this like a big pool. And as a result, the machine can learn very poorly, and and also it's not data safe, AI safe, because for those important like data, if you are not finding them, the machine will be like poorly trained and can have very can have disaster like results when you actually implement those. And this is the like a picture of Tesla crash into a like overturned track because of the like a poor train of the machine. So our idea by implementing the active learning is just have a small change by letting the machine to decide what data it want to learn and ask the label from the like the expert. And in this way, the machine can learn most efficiently because he knows what he wants to improve itself. And the result is it result in like a AI safe like a machine learning process, and also end up with much less data need to be annotated by the expert. So it reduces the cost of annotation, data annotation. And here's the basic, like a very general intuition of what type of data a machine want to learn. So on the left, assume the machine already learned some of the pictures about mobile data, mobile phone, and he want to learn more to recognize a mobile phone from the picture. So what interest is in most? Basically, there are two types of like, samples you want to learn. First is called the out of distribution samples. So they are mobile phones, but they looks much like different than the current knowledge of possessed by the machine. And the second type is the confusing samples. So they look very similar to the like a mobile phone, but they are actually calculators. So our design of active learning aims to find these two types of like samples, and by learning those, the machine gonna improve in the most efficient way. And here are some preliminary results that shows the out of distribution samples and the confusion samples from the real world. And you can see that out of distribution samples, usually they are written in a very different way than their like own kind. And the confusion samples, each character looks like very confusing. Can be multiple like types of characters. So by applying the active learning, we can see that to achieve the same accuracy, if you implement active learning, you end up requires less than 100 samples for label. But if not, you just have like more than 200 samples need to be. Sorry. And to sum up, there are some like useful tools we use to address those active learning problems: the probability theorem, the information theorem, and the optimization methods. Okay, so to sum up, the take-home message for you is just first, a lot of machine learning algorithms nowadays driven by the big data, and data annotation can be a very tedious process. And applying active learning can reduce such high labeling costs. And in this process, human does not decide what to teach, but machine manage to decide what to learn. So next time you visit the office hour, you can consider yourself as a practitioner of active learning because you decide what to learn by yourself. That's all for the talk. Thank you.
Great. Thanks, Richard. Let's transition to the next student.
Okay.
Hello everyone, it's me Hitesh, Sapkota, PhD fourth year student. working under the supervision of Professor Dr. Ji. Uh, Today, I'm going to briefly discuss about what is the multiple instance learning approach and what are the some limitations in the existing approach and how we have deal with those limitations. So first, I would like to introduce some problem scenario. So if you look to the left side of the slide, so you can see there's one abnormal video,
Because
and
you are not showing that slides. Probably you can. This is different. This is still the first slide.
oh, mm, sorry, I may need to.
That's good. Now it is good. Yeah, excellent.
Uh, do I need to start over?
It's okay. Just continue. That's fine.
Yeah. So if you look to this slide, so in the left side, so there are two videos. One is abnormal video, and another one is normal video. So basically, abnormal video consists of abnormal frames as well as normal frames, whereas normal video consists of normal frames. So basically, when I say abnormal, so that means some kind of abnormal activity going on here. So basically, if you look to this figure, so you can see that there is explosion going on here. So that means this frame is referred as abnormal frame. And if you look to the right side, so there is frame that doesn't contain any abnormal activity. That's why it's regarded as normal frame. So basically, the problem scenario is that we are going to have abnormal and normal videos, and our goal is to devise the model that can correctly classify each frame, saying that whether the particular frame is abnormal type or normal type. So basically, one simple approach that we can think of is that first let's collect the videos corresponding to abnormal and normal type, and then let's annotate each frame within that video. And then once we get the annotation for each frame saying that whether it's normal type or abnormal type, then we can use some fully supervised learning approach by treating this problem as binary classification problem. But the problem associated with this is that since we know that the video may contain many number of frames, and annotating each frame level is going to be time consuming. That's why there comes the role of multiple instance learning. So basically, the idea in the multiple instance learning is that let's not use the frame level annotation. Let's let's only use the video level annotation. So when I say video level annotation, that means we only use the information regarding whether the video is normal type or abnormal type, and we are going to uh, like train the model by just relying on that video level annotation. So basically, the benefit of this approach is going to be we are going to save a expensive labeling costs, because compared to the frame level annotation, video level annotation is going to be cheaper. So basically, in contrast to the fully supervised learning approach, there is different setting in multiple instance learning. So basically, in the MIL setting, let's consider each video is treated as bag, and each frame or corresponding with that videos are going to be treated as instances. So basically, in the multiple instance learning, we are going to have two type of bags. So one is positive bag and another one is negative bag. And in the positive bag, so we there is going to be at least one positive instance. So positive instance is same as abnormal frame in the video scenario. So basically, for the positive bag, we'll have at least one positive instance, and for the negative bag, all of the instances are going to be of negative type. So that is regarded as standard MIL assumption. So basically, in summary, so there exists at least one positive instance in the positive bag, and all the instances in the negative bag are of negative type. Now I would briefly discuss about some existing maximum based MIL approach. So basically, you can see that so there are the bags, so positive bag and then a negative bag, and there is one machine learning model. and we have output corresponding to each instance. So basically you can see the scores, right? So this score indicates the probability of particular instance being positive. So basically the existing maximum ML based approach tries to maximize the maximum score from the positive bag and the maximum score from the negative bag. So you can see in the figure, the maximum score is 0.9. So basically it takes the 0.9 and maximum score from the negative bag is 0.4. So basically the gap is going to be 0.5. So basically the objective in the existing approach, maximum based approach, is going to maximize this gap. However, so like there are like two main key limitations that exist in the existing maximum based approach. So before presenting those limitations, I'd just first like to explain those two figures. So basically in the upper figure, you can see that there are two persons and it looks like they are fighting. So basically this frame like is similar to fighting related abnormal activity, but in fact this is the normal frame, right? So and also if you look to this frame, so basically it looks like it is the frame related to arson, but it's actually normal type. So basically when I say outlier, so that means the normal frames that looks like other abnormal activity types, so those are the outlier scenario. And if you look to this figure, so there are like two frames. So those frames are from the same video, but they consist of different abnormal types. So basically if you look to this frame, so there is a person running. So basically this is the running related abnormality. And if you look here, so this is the loitering related abnormality. So that means in the same video, so there are two different types of abnormality, and this scenario is called multimodal scenario. So in the existing maximum based approach, since it's only considering the maximum, like the instance with the maximum score from the positive bag, so it's likely to be like influenced by the outlier scenario, and also by the also if there is multimodality, and it's likely that it's going to miss one of the like abnormality type, because it only cares about a single instance. That's why the problems are like the existing approaches are going to be sensitive to outlier and multimodal scenario. Now, so basically like to address those limitations, we propose like various approaches, and I'll briefly explain the key idea behind those approaches. So basically, like instead of considering the single instance, let's consider the multiple instances from the positive bag, and then let's try to maximize the gap between average of those like multiple instance like value to be higher than that of the maximum score from the negative bag. So in like summary, so basically what we do is that we take the like top k, or like highest predicted like instances from the positive bag. For instance, in this case we have 0.9, 0.6 and 0.5. So basically we take the average value of this to be higher than the maximum value of this. So basically this facilitates the involvement of the multiple instance from the positive bag. So that makes the approach more robust to outlier and multimodal scenario, because since we are including the multiple like instances from the positive bag, that's why like it's likely that it's going to capture the multiple types of abnormality type, and also like the effect of outlier is going to be minimized. So basically this is the experimental result from one of our proposed approach. So MMIL refers to the maximum based approach, and RLMIL indicates the our proposed approach. So AUC, so in this case we are using the AUC score. So basically AUC score indicates the degree of separability between positive and negative instances in terms of their like output score. So the higher the AUC score, the better. So you can see that our proposed approach has much more better like performance compared to the maximum based MIL approach. So just to demonstrate some like qualitative results, so you can see this figure. So this is the outlier case, so where we have arson related activity going on here. Like it looks like arson related activity going on here, but it's not, it's actually the normal frame. So that's why this is the outlier. So if so during the prediction of this particular frame, maximum based approach fails to predict this as normal, but our approach like can correctly classify this as like normal frame. That's why our approach is like more robust to outlier. And another one is, this is the multimodal scenario. So you can see that there are like two frames and they are from the same video. So first frame refers to the like running related abnormality, and second refers to the walking in the wrong direction related abnormality. So basically our results shows that like our approach is able to correctly classify both frames as abnormal. Whereas if we use maximum base, it can only correctly classify the first frame as abnormal. And for the second frame, the maximum based approach just tells this as like normal frame, and that is wrong. So that's why our approach is more robust to multimodality. So in conclusion, I briefly introduced the problem associated with fully supervised approach. Then I presented some existing MIL approaches along with limitation, and then I propose a new approach in order to address these limitations. And finally, I demonstrated some results to show the effectiveness of our proposed approach. Thank you.
Great, thanks, Hitesh. Yeah, let's move on to the next student.
Can you see the screen?
Yes, please go ahead.
Okay. So hello everyone, I'm Deep and I'm here to give a high-level overview of meta learning and the research work we've carried out in the field of meta learning. Basically, deep learning models have achieved significant results in various tasks ranging from classification to video analysis to and many other tasks. But the deep learning models usually require large amount of training data to get a good performance. Basically, in deep learning models, we use large number of training data to solve a problem where we require, for instance, in classification problem, we require image and label, and using those image and label, we train the deep learning model. But many real world problems have limited data. For example, medical diagnosis or rare species classification or drug discovery. For instance, for some disease, we might not have enough images or enough doctors and expertise to get labels for all the medical conditions. Further, in many cases, it is expensive to get labels for such for the data instances. For instance, in drug discovery, to get each training instance, we need to carry out experiments, and which may take both a large number of resource and also may require a long time to get label for a single instance. So, in such limited data problems, the problem becomes to learn from few examples of a task to make prediction for nuance in examples on that task. For instance, this would be a limited data problem where we need to classify between two classes, dogs and otters, and we just have 4 instances per class, and we need to classify new instances. If we directly apply deep learning models, then the deep learning models will overfit to such limited data problem, and simply using off-the-shelf regulations are not effective in such problems. So for such problems, we can use meta learning. Basically, to learn from limited examples of a task, we could use meta learning, where we consider large number of tasks or task distribution, uh, and the tasks share some common knowledge. Basically, we consider large number of similar tasks with a few examples in each of those tasks. Like one of the basic assumptions is that uh, the tasks share some common knowledge, and in meta learning, we learn in two levels, one in meta level and one in task level. We basically try to learn the shared knowledge across various tasks and use this shared knowledge across all the tasks to perform well on a specific task. Basically, this is the idea of meta learning, that is to learn in two levels, going one level ahead to learn the knowledge that is shared across the task. Basically, I will first describe the basic setup in meta learning. In meta learning, we consider large number of tasks, and the each task is a learning problem. Basically, in each task, we are given a limited data, and using this limited data, the model is to perform well on the specific task, which is evaluated using the query set. Basically, this support set is the information available to learn, and this query set is used to evaluate the model. The key problem is to correctly classify or correctly predict for the query set after learning on the support set. Uh, that all the information from both the support set and query set can be used during the training phase, whereas in test phase, we evaluate the model on the different test tasks. So various approaches in meta learning have been and proposed. Here we discuss three main approaches. One of the most successful approach is optimization based approach. Basically, in optimization based approach, the idea is to learn model parameters such that the model can adapt to new tasks using few optimization steps and limited examples alone. For example, uh, here we present model agnostic meta learning or MAML, which is one of the most successful optimization based approaches. Like the idea is to learn a good initialization from large number of training tasks so that the model can adapt to each of the tasks using few examples and few optimization steps. Kind of like we would be learning a good initialization using large number of tasks. This initialization would be shared across all the tasks, and using this initialization, the model could adapt to the all new test tasks. So one of the areas we are working on is to improve this MAML. Basically, MAML, uh, though MAML learns a good initialization, but since it is learning from limited examples, just few examples, the predictions for different tasks may not always be reliable. One of the problem then becomes whether we can quantify the model's prediction uncertainty for such tasks. There have been some works to address that issue, but they are either computationally expensive or make strong assumptions. We use ideas from subjective logic to extend the MAML model to have the uncertainty capability. Basically, the MAML model just uses a softmax layer. Basically, it outputs probability values for different classes and does not have a mechanism to show the confidence in the predictions. For instance, in two-class classification problem, the model may output the probability for different classes, but it does not output how confident it is in this prediction. We use ideas from subjective logic where we introduce vacuity, the degree of confidence, and basically the model can output the belief for different classes along with the vacuity, that is the lack of evidence. Basically, if there is high vacuity, then the model is not at all confident on its prediction and the prediction cannot be trusted, that is model is uncertain. Whereas if it is not vacuous, the vacuity value is low, then we can trust the model's confidence. So basically, our idea is to learn a good initialization which makes good prediction, but also can output the confidence in the prediction along with the good initialization. Using that good initialization, and another problem with MAML is like it uses a large number of tasks to learn the good initialization, and learning on each task is a computationally expensive process. So basically, we propose to perform task selection for the MAML model, where we select the most informative tasks based on the uncertainty score. Basically, we consider a large number of tasks and select those tasks which are informative. The informativeness of tasks is defined based on the uncertainty value in the task. With these improvements, we carry out some experiments, and basically the black curves show the results without any task selection, whereas the blue curves are with task selection. Basically, the task selection seems to help the model achieve better generalization and faster generalization. Uh, Next, we evaluate our model's uncertainty capabilities, and we see that basically the model has to learn from the support set and predict on the query set. Basic MAML model would not be able to output the level of confidence in its predictions, but with our proposed method, we can output both the prediction and the degree of confidence as indicated by vacuity. Basically, the red colors indicate the predictions which are incorrect. Basically, for incorrect predictions, the vacuity value is quite large, and which shows that our model can correctly capture the uncertainty. Next, uh, for out of distribution instances, basically, if we rotate the query set instances, then the accuracy drops, is shown in the cover, but the vacuity value increases. showing that model is not confident at all for out of distribution instances. Similar experiments are carried out for different data sets, and we see similar results. Basically, the model has to learn from just the limited instances of the support set, and for the query set, the vacuity represents the level of confidence in its prediction. For OOD instances such as this and this, the model outputs high vacuity, whereas for the in-distribution instances on which the model is confident, the model outputs correct prediction as well as vacuity, which shows our model's capability. Further, we carry out another experiment where we use different vacuity thresholds and see the accuracy. As we use different vacuity thresholds, the model's accuracy increases, and this is one of the works that we have currently done. There are other meta-learning approaches as well, such as metric-based approach. Basically, in metric-based approach, the key idea is to learn an embedding function using large number of training tasks, so that the meta learning is more efficient in the new embedding space. For instance, this figure shows a metric, one approach of matching networks. The idea is to be learn a good embedding function so that we can perform well on the new test tasks in that embedding space. One of the areas that we are thinking of is to extend such metric-based approaches to have uncertainty capabilities. Another approach is like neural process-based approach. Basically, neural process-based approach, we also combine benefits of neural networks and Gaussian process. Basically, these approaches are used for, these approaches can solve meta-learning problem, that is learning from few instances, but there are some limitations in such approaches, such as handling heterogeneous tasks. Basically, one of the ideas we are thinking about is that not all tasks may be equally related. Some tasks may be more related than others, and this is one of the areas that we are currently working on. Thank you. Any questions?
Great, thanks, Steve. Yeah. Let's move on to the next student. Yeah.
Good morning. I'm going to talk about multimodal data fusion, and I will briefly introduce what is multimodal data and why do we analyze multimodal data, and I will briefly introduce one of our work. So what is multimodal data? So that's the data from multiple modalities. And when talking about modality, most people refer to the sensory modality that is the primary form of human sensation. So in our daily life, we see objects, hear sounds, feel the texture, and smell odors and taste the flavors. And we use all these modalities to help make decisions and take action. But for machine learning, the modality is usually referred to a certain type of information and the representation format in which the information is stored. So in other words, we focus on how the data is stored. So here are some illustrative examples of the data modalities. So one is the natural language. It could be spoken, which is stored as audio, or it could also be the written language, which is stored as text. And the second type is visual. It could be image, or it could be video, which is essentially a sequence of images. And it could also be auditory, such as sounds and music, which are stored as audio. And there are other types of data modalities, such as the data collected from the medical or robotic domains. And these data are stored in some specific format. And I will introduce some real-world tasks tackled by the multimodal learning. So the first task is audio-visual emotion recognition. So given the video recording of human social interactions, such as a group of people gathering together, we hope that a machine learning model can detect the human facial behavior and recognize the emotions of each people. So the input to our model is the video recording of human social interactions, and we extract the images and audios from the video recordings. So these are the two data modalities. And the second task is audio-visual speech recognition. So you may be familiar with speech recognition. That is, given the audio of human speech, a machine learning model aims to transcribe it into text. However, some parts of the speech may be difficult to recognize. So in this case, we may need lip reading to help identify those parts and understand what the speaker is saying. So the input to our model is the video recording of human speech. And similarly, we extract the images and audios from the video recordings. That's the two modalities. And the third task is visual question answering. That is, to given an image and also some questions, we expect the model can answer the question. So for instance, given the image of a man and a woman, and given a question, who is wearing the glasses? We hope that the model can answer whether it is the man or the woman. So the input of our model is the image and the text. That's the two modalities. The fourth task is action recognition, which could be the most difficult task among the four tasks. And it is essentially the identification of different actions from the video clip. So the input to our model is the video recording of human actions. And similarly, we extract the image and audio, and we hope that the model can make the prediction of the action type. Now, why do we need multimodal data, and why do we analyze the multimodal data? The primary motivation is that the data from multiple modalities are usually semantically correlated, and they are very likely to provide complementary information to each other. So the multimodal data reflects patterns that are not usually visible if we only work with individual modalities. So a machine learning model that consolidates multimodal data is expected to produce better predictions in terms of higher accuracy or more robust noisy data. And I will briefly introduce one of our work, which is titled Dynamic Fusion of Eye Movement Data and Verbal Narrations in Knowledge-Rich Domains. So the knowledge-rich domains refers to the domains that requires the knowledge of some specific or specialized discipline or profession. In other words, it's not the general knowledge. So for instance, it could be the medicine domain or science domain or the security intelligence domain. And we perform a case study of visual-based decision-making for experts. So we have a group of physicians who are specialized in dermatology, and they view the medical images of skin lesions, and they verbally describe the disease, and finally makes a diagnostic decision. So the data we have contains two modalities. One is the eye movement recorded by the eye tracker, and the second modality is the verbal narration transcribed as text. And our goal is to build a model that can fuse the multimodal data and answer the following questions. What are the latent patterns of eye movement and verbal narrations? How the latent patterns from each modality are related? And are these latent patterns useful for diagnostic decision making? So due to the time limit, I will focus on the first question. And I will use an illustrative example to explain the important findings about latent patterns from the two modalities. So in this case, let's take a look at the figure. So given the image, a physician describes the image, and the verbal narration is recorded and shown in the middle part of the figure. So it starts with, so this is someone's either an elbow or knee, probably an elbow. So our model can automatically partition the verbal narration into three phases: the description, reasoning, and conclusion. as shown in the left part of the figure. So the description phase, as you can see, it aligns with the verbal narrations describing how the lesions look like. And the reasoning phase aligns with the verbal narrations with what can be inferred from the image. And the conclusion phase is the final diagnostic decision. And also, our model can automatically group words from those verbal narrations into topics. And we use different colors to highlight the different topics. So for instance, the words highlighted in pink are corresponding to the body location, such as the elbow, knee. And the words highlighted in orange are corresponding to the disease morphology, such as nodular lesions and discrete yellow papules. And again, our model can automatically group the eye movement events into 3 patterns, namely the concentration, switching, and clutter, as shown in the second, third, and fourth image from the figure. So we use the visualization technique to visualize the eye movement pattern. As shown in the second, third, and fourth image, we use circles to denote the fixated location. And we use line to connect 2 fixated locations. And the concentration pattern, which is shown in the second image, corresponding to the fixation on a small area. And the switching patterns are essentially switching between the 2 locations. And the clustering pattern are essentially the eye gaze covering a large area. So in summary, we build a machine learning model to consolidate multimodal data in order to produce better predictions in terms of higher accuracy or more robustness to the noisy data. This is because the data from multiple modality are usually closely related to each other. And here are some references. If you are interested in, you can just check it online. These are the interesting tutorials for the multimodal machine learning. And thank you for your audience.
Great, thanks, Minxun. I think that concludes all the presentations. So I would like to thank all the presenters to talk about those interesting, important research areas. So for more topics and other information about our lab, you can visit rit.edu/mining, which is our lab website, which provide more information about our research. We hope this will be of interest to our undergraduate students and other students who are interested in AI machine learning. Okay.